Hello there, and welcome to the Scientist Sleepy. Does the idea of an ending, a finality, ever stir a quiet unease within you? Tonight, we gently turn our gaze towards one of the most profound and perplexing possibilities for our universe: the final black hole, the potential end of time itself. It's a concept that stretches the limits of our imagination, inviting us to explore the ultimate destiny of everything we know, not with fear, but with a deep and peaceful curiosity. So settle in, allow yourself to become as comfortable as you can possibly be, and let the weight of the day gently begin to lift. If you find this journey into the cosmos soothing, consider giving this video a like and subscribing to the Scientist Sleepy. It's a simple act that helps us continue to craft these quiet havens for wonder and rest. And as we embark on this exploration, I invite you to share in the comments below. What is one small, beautiful thing you notice today? Your reflections, like the cosmic processes we'll discuss, are part of a grander tapestry. Now let us drift towards the edge of the observable and beyond. The universe began with a singular point and may end with one. Our cosmic journey began, as far as our current understanding allows, from an infinitesimally small, incredibly dense point known as the singularity. This was the genesis of the Big Bang, the explosive expansion that birthed space, time, matter, and energy as we know them. It was a moment of ultimate condensation, a point from which everything unfolded. Now, as we peer through the lens of theoretical physics and cosmological models, we find ourselves contemplating a potential end to this grand cosmic drama that mirrors its beginning: a return to singularity, or rather, a universe ultimately defined by them. The concept of the final black hole paints a picture of a cosmos that, after eons of expansion and stellar decay, becomes dominated by these enigmatic celestial objects. Imagine a universe where the last stars have long since faded, their fuel exhausted, their light extinguished. The grand cosmic tapestry, once vibrant with nebulae and galaxies, has dimmed to an almost unimaginable degree. In this twilight realm, black holes, born from the collapse of massive stars or perhaps from earlier cosmic epochs, would persist. They are the ultimate remnants, the enduring structures in a universe that has otherwise wound down. The sheer, relentless pull of their gravity would become the defining force. And at the heart of each black hole lies another singularity, a point where the very fabric of space-time is thought to be infinitely curved, a place where our current laws of physics cease to apply. This theoretical endpoint, where the universe is a vast, cold expanse populated by slowly evaporating black holes, each containing its own inscrutable singularity, brings us back to the idea of a singular origin. It suggests a cyclical nature to existence, or at least a profound symmetry between creation and annihilation, between the ultimate beginning and the ultimate end. The journey from a single point of infinite density to a universe filled with countless, yet slowly diminishing, points of infinite density is a thought that humbles the mind and expands the soul. It is a reminder that the most profound truths about our existence may lie in the grandest scales, in the overarching narratives that govern the cosmos. And so, from a singular beginning, the universe may ultimately resolve into a multitude of singularities, a silent, echoing testament to the profound symmetry of cosmic existence. The universe began with a singular point and may end with one. Our journey into the profound mysteries of the cosmos often begins with a question that echoes through the ages: what was before the beginning? And perhaps more unsettlingly, what lies beyond the end? Science, in its relentless pursuit of understanding, offers us glimpses into both, weaving a narrative that is as awe-inspiring as it is humbling. We speak of the Big Bang, the moment from which all of space, time, matter, and energy is believed to have sprung. But to truly grasp the immensity of this event, we must first consider the very nature of that initial state. It wasn't merely an explosion asterisk in asterisk space, but rather the rapid expansion asterisk of asterisk space itself. Imagine, if you will, a point of unimaginable density, a state so compressed that our current laws of physics falter and cease to describe it. This is the singularity, a concept that stretches the limits of our comprehension. It is a state where all the vastness of our universe, every star, every galaxy, every particle was contained within a volume infinitesimally small. To visualize, this is to grapple with the very essence of existence compressed to its absolute limit. This initial singularity, the progenitor of everything we perceive, is not just a theoretical construct. It is the bedrock upon which our current cosmological model is built. It represents the ultimate beginning, a point from which the universe unfurled its grand tapestry. But the story of cosmic beginnings is inextricably linked to its potential endings, and it is here that the symmetry of creation and dissolution begins to reveal itself, hinting at a cyclical, or at least a profoundly interconnected, cosmic destiny. The very forces that initiated the universe may, in their ultimate grand conclusion, lead it back to a state eerily reminiscent of its genesis. This is not a simple repetition, but a profound echo, a cosmic resonance that speaks to the fundamental principles governing reality. The universe in its infinite complexity may be a grand cycle, a cosmic breath inhaled and exhaled, a testament to the elegant and sometimes startling simplicity of fundamental laws. The idea of a singular point as both the origin and the potential terminus is a powerful one, suggesting a universe that is not merely a fleeting event, but a continuous, self-referential process, a grand cosmic dance of becoming and unbecoming. This initial singularity, this point of infinite density, is the ultimate mystery at the heart of our universe's inception, a concept that continues to challenge and inspire our quest for knowledge, reminding us that the most profound truths often lie at the boundaries of our understanding, in the very points where our current paradigms break down. As we contemplate the immense journey from that primordial point of infinite density, we discover a breathtaking symmetry. The universe, in its genesis, was a singularity, a state of ultimate compression. And as we peer into the potential futures of this vast cosmos, scientific inquiry points towards a similarly extreme, yet paradoxically opposite, endpoint. It is a concept that, while still debated and explored, offers a profound perspective on the nature of existence and the ultimate fate of all that we know. The initial singularity of the Big Bang was a point of infinite density and zero volume, a state from which space and time themselves emerged. Now, consider the vast stretches of time and the immense distances that lie ahead. The universe is not static. It is dynamic, ever-expanding, and its ultimate destiny is a subject of intense scientific fascination. While various scenarios are proposed, one of the most compelling, and indeed the one that connects most directly to our theme of final black holes, is the notion of a universe that eventually succumbs to a state of ultimate emptiness and cold, a process that itself involves the gradual dissolution of all structures, including the very black holes we are exploring. However, before we reach that ultimate cold diffusion, the concept of a final singularity emerges. This isn't necessarily a reversal of the Big Bang in a temporal sense, but rather a convergence of all matter and energy into a state of extreme density, much like the initial singularity, but achieved through a different cosmic mechanism. The most prominent pathway to such a state involves the ultimate fate of black holes. Black holes, as we will explore, are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are the cosmic behemoths, the ultimate gravitational prisons. And as the universe ages, as stars burn out and galaxies drift apart, these black holes will remain, slowly consuming any stray matter and energy. The theory of Hawking radiation suggests that black holes are not eternal. They slowly evaporate over unfathomably long timescales. But for the vast majority of their existence, they are dominant forces. In some cosmological models, particularly those that might involve a reversal of cosmic expansion or a universe that collapses back upon itself, the Big Crunch scenario, though less favored now, the ultimate fate could be a convergence of all matter and energy into a single, infinitely dense point, a final singularity, mirroring the initial one. Even in scenarios where the universe continues to expand indefinitely and eventually succumbs to heat death, the lingering remnants of the universe might be the supermassive black holes, slowly fading through Hawking radiation. If one entertains a cyclical model of the universe, where a big crunch leads to another big bang, then the end, singularity, becomes the beginning singularity, a continuous cosmic breath. The very concept of a final black hole implies a universe that has largely ceased to be, a cosmos where these gravitational titans are the last vestiges of activity, slowly dissolving into the void. The idea that the universe might begin and end in a state of such extreme condensed form is a profound testament to the fundamental laws that govern existence, suggesting a cosmic narrative that is perhaps more circular, more interconnected than we can easily perceive. It's a thought that invites us to consider the vast sweep of cosmic time, not as a linear progression, but as a grand, unfolding pattern, where beginnings and endings are not necessarily absolute separations, but rather points of profound, echoing convergence. This echo from the beginning to the potential end, this symmetry of a singular point, is a quiet reminder that the grandest narratives of existence often begin and conclude in the most condensed, most fundamental states, imbuing the vastness of the cosmos with a sense of profound, cyclical elegance. Black holes are not holes, but rather incredibly dense points of gravity. It is a common misconception, perhaps born from the very name, to envision a black hole as an empty void, a cosmic chasm into which things simply fall and disappear without a trace. But the reality, as illuminated by the elegant framework of general relativity, is far more profound and, in its own way, more tangible. A black hole is not an absence of matter, but rather an overwhelming presence of it, compressed into a region of spacetime so infinitesimally small that its gravitational pull becomes absolute. Imagine taking a star many times the mass of our Sun and squeezing it down, not to the size of a planet or a city, but to a point smaller than an atom. This is the essence of a singularity, the theoretical heart of a black hole, a place where all the mass that once constituted the star is concentrated. It is this extreme concentration of mass, this incredibly dense point, that dictates the black hole's characteristic properties. The gravitational field generated by such a concentrated mass is so immense that it warps the very fabric of spacetime around it to an extraordinary degree. Spacetime, as described by Einstein, is not a passive backdrop, but a dynamic entity, a four-dimensional continuum that is influenced by the presence of mass and energy. In the case of a black hole, this influence is so profound that it creates a region from which nothing, not even light, can escape. This is why they appear black to us. They absorb all incident radiation and reflect none. The boundary of this region, the point beyond which escape becomes impossible, is known as the event horizon. It is not a physical surface in the traditional sense, like the surface of a planet or a star, but rather a boundary in spacetime defined by the strength of gravity. Once an object or a particle crosses this invisible threshold, its fate is sealed. It is inexorably drawn towards the singularity at the center. The density within a black hole is so extreme that our current laws of physics, as we understand them, begin to break down at the singularity itself, hinting at the need for a more complete theory, perhaps one that unifies gravity with quantum mechanics. But even without fully comprehending the singularity, the immense gravitational force originating from this hyperdense point is the defining characteristic of a black hole, shaping the cosmos around it and serving as a stark reminder of the universe's capacity for extreme conditions. Within this cosmic enigma, gravity reigns supreme, not as an emptiness, but as the ultimate, inescapable embrace of concentrated existence. The event horizon is the point of no return for all matter and energy. Imagine, if you will, a cosmic boundary, not a physical wall, but a conceptual divide that marks a profound transition. This is the event horizon of a black hole, a place where the fabric of spacetime is so dramatically warped that escape becomes not just difficult, but utterly impossible. It is a threshold, a one-way door into the abyss. The nature of this boundary is intrinsically linked to the extreme gravity generated by the black hole's concentrated mass. As an object, be it a star, a planet, or even a photon of light, approaches this horizon, the gravitational pull intensifies with an unimaginable ferocity. For anything crossing this invisible line, the future is irrevocably set, a trajectory directed inward, towards the singularity at the black hole's heart. The speed required to escape such a pull would need to exceed the speed of light, a feat that, according to our current understanding of physics, is impossible. Therefore, the event horizon acts as the ultimate cosmic trapdoor. It is a surface from which no signal, no information, no particle, not even light itself, can ever return to the outside universe. This is why black holes appear black. They absorb all light that falls upon them, reflecting none. The size of this event horizon is directly proportional to the mass of the black hole. A smaller stellar black hole will have a relatively small event horizon, perhaps only a few kilometers across, while a supermassive black hole at the center of a galaxy might have an event horizon spanning billions of kilometers, larger than the orbit of our own solar system. The concept of the event horizon is not merely theoretical. It is a fundamental consequence of Einstein's theory of general relativity, a theory that has been tested and verified in numerous ways. While we cannot see the event horizon directly, its effects on surrounding matter and light are observable, providing strong evidence for its existence. For instance, the swirling disks of gas and dust around black holes, known as accretion disks, emit intense radiation as they spiral inward, a phenomenon that is a direct consequence of matter being accelerated towards the event horizon. The very act of observing these accretion disks and the gravitational lensing effects around black holes allows us to infer the presence and properties of these enigmatic boundaries. The event horizon represents a cosmic boundary where the laws of physics as we experience them in the wider universe begin to diverge, leading to a realm of ultimate consequence. Within its invisible embrace, the event horizon whispers a timeless truth, that some journeys, once begun, have no return, leaving us to ponder the profound finality of cosmic boundaries. Singularities are theorized points of infinite density at the heart of black holes. At the very core of a black hole, where the gravitational pull becomes infinitely strong, lies a concept that challenges our very understanding of physics: the singularity. Imagine all the mass of a collapsed star, or even a supermassive galactic center, compressed into a region of space so infinitesimally small that it approaches zero volume. This is the essence of a singularity. Our current models, particularly Einstein's theory of general relativity, predict that such a point must exist within every black hole. It's a place where the fabric of space-time, as we understand it, is stretched and distorted to its absolute limit, and then theoretically breaks down entirely. The mathematics involved become paradoxical. Density, curvature, and tidal forces all tend towards infinity. This is why singularities are not directly observable. They are hidden, shielded from our universe by the black hole's event horizon, the boundary beyond which nothing, not even light, can escape. This protective veil is crucial, as it prevents the infinite densities and curvatures of the singularity from propagating outwards and disrupting the rest of space-time. However, this also means that the singularity remains one of the most elusive and fascinating mysteries in astrophysics. What truly happens at this point of infinite density? Does space-time cease to exist? Does matter itself get annihilated, or is it transformed into something entirely new? These are questions that push the boundaries of our current scientific knowledge. General relativity, while incredibly successful in describing gravity on large scales, is known to break down in extreme conditions, such as those found at the singularity. Physicists believe that a more complete theory, perhaps a unified theory of quantum mechanics and gravity, is needed to fully comprehend what transpires at the heart of a black hole. Some theories propose that instead of an infinitely dense point, there might be a region of incredibly compressed, but finite matter, governed by quantum effects. Others suggest that the singularity might be a gateway to another universe, or a point where time and space are fundamentally different. The very idea of infinite density is difficult for our minds to grasp, as our everyday experience is with finite quantities. Yet, in the extreme environment of a black hole, the universe seems to present us with phenomena that defy our intuitive understanding. The singularity represents a frontier of our knowledge, a place where the rules of the cosmos as we know them may no longer apply, and where the very nature of reality is called into question. It is a testament to the universe's capacity for the extraordinary, a point of ultimate compression and ultimate mystery, existing in the deepest, darkest recesses of space. Within the silent, crushing embrace of a black hole lies a point where all physical laws converge into a profound, unknowable stillness, a silent testament to the universe's ultimate compression. Hawking radiation suggests black holes are not truly eternal, but can evaporate. For a long time, the prevailing scientific understanding painted black holes as ultimate cosmic prisons, singularities from which nothing, not even light, could escape. They were seen as eternal entities, forever consuming matter and energy, their gravitational pull an unyielding force. This perspective, while awe-inspiring in its depiction of cosmic power, left a lingering question. Could such absolute dominion truly persist for all of eternity? The answer, as revealed by the groundbreaking work of Stephen Hawking, is far more nuanced, and in its own way, even more profound. Hawking radiation proposes a mechanism by which black holes, over unfathomable timescales, can actually diminish, even disappear. This concept arises from the peculiar nature of quantum mechanics, which operates at the very smallest scales of reality, and its intersection with the extreme conditions near a black hole's event horizon. At its core, Hawking radiation is a consequence of quantum fluctuations in the vacuum of space. Even in what appears to be empty space, the laws of quantum physics dictate that pairs of virtual particles and antiparticles are constantly popping into existence and then annihilating each other an instant later. These fleeting pairs, a particle and its antimatter counterpart, arise from the vacuum energy. Normally, they exist for such a brief moment that their annihilation is instantaneous, leaving no lasting trace. However, when such a particle-antiparticle pair forms precisely at the edge of a black hole's event horizon, something extraordinary can happen. One particle might fall into the black hole, while its partner, if it gains enough energy from the gravitational field, can escape. This escaping particle, now a real particle rather than a virtual one, carries away energy from the black hole. From an external observer's perspective, it appears as though the black hole is emitting radiation. This emitted radiation is known as Hawking radiation. Crucially, the energy carried away by this escaping particle is equivalent to a tiny fraction of the black hole's mass. According to Einstein's famous equation, E equals mc2, mass and energy are interchangeable. Therefore, as a black hole radiates energy, it loses mass. This mass loss, though minuscule for stellar mass or supermassive black holes in the present universe, means that black holes are not static, eternal objects. They are slowly, imperceptibly, but inexorably, losing mass and energy. The rate at which a black hole evaporates is inversely proportional to its mass. Smaller black holes evaporate much faster than larger ones. For a black hole with the mass of our Sun, the evaporation process would take an estimated 1067 years. For a supermassive black hole, the number is astronomically larger, well beyond the current predicted lifespan of the universe itself. However, for hypothetical, very small primordial black holes that might have formed in the early universe, their evaporation could be occurring even now, potentially ending in a final burst of energy. This process of evaporation represents a fundamental shift in our understanding of black holes. They are not merely passive sinks of matter and energy, but dynamic entities that interact with the quantum vacuum and, over immense cosmic epochs, can cease to exist. The very idea of a black hole's end, however distant, introduces a form of cosmic impermanence to even the most seemingly immutable objects in the universe. And so, the eternal prisons of our imagination reveal a secret, a slow, quiet fading, reminding us that even the most absolute forces in the cosmos are subject to change, a gentle surrender across unimaginable spans of time. The lifespan of a black hole is incomprehensibly vast, far exceeding the current age of the universe. Imagine, if you will, a cosmic clock, not ticking in seconds or years, but an eon stretching beyond our wildest imaginings. The black holes we observe today, those enigmatic voids that warp spacetime and swallow light, are, in human terms, remarkably ancient. Yet their true existence, their tenure in the grand cosmic theater, is measured on a scale so immense that our current understanding of time begins to feel like a mere flicker. When we speak of a black hole's lifespan, we are not talking about billions of years, but trillions upon trillions, and then some. The process by which a black hole might eventually cease to exist is through a phenomenon theorized by Stephen Hawking, known as Hawking radiation. This is a slow, incredibly gradual emission of particles from the event horizon. For a stellar mass black hole, the kind formed from the collapse of a single star, its lifetime is estimated to be around 1067 years. To put that into perspective, the current age of the universe is approximately 13.8 billion years, which is 1.38 x 1010 years. The difference is staggering. It is a number so large that it dwarfs the number of atoms in the observable universe. For a supermassive black hole, the colossal entities found at the centers of galaxies, like our own Milky Way's Sagittarius A, their lifespans are even longer, potentially reaching 10–100 years or more. These gargantuan objects, with masses millions or even billions of times that of our Sun, are so profoundly dense and possess such immense gravitational pull that the rate at which they lose mass through Hawking radiation is infinitesimally slow. Think of a single drop of water falling into an ocean that is continuously being replenished. The evaporation process is so protracted that for all practical purposes, these black holes are eternal on the timescales relevant to human civilization, or even the entire history of life on Earth. Even after all the stars have burned out and all galaxies have dispersed, these cosmic behemoths will continue to persist, slowly, painstakingly shedding their mass. The universe, in its current form, will have long since transformed into a cold, dark, and nearly empty expanse before the last vestiges of the largest black holes begin to truly fade. This immense longevity underscores the profound stability and enduring nature of these cosmic entities, offering a stark contrast to the ephemeral existence of stars and planets. It speaks to the deep, fundamental forces at play in the universe, forces that operate on scales that challenge our intuitive grasp of reality. The sheer duration of a black hole's existence is a testament to the power of gravity and the slow, inexorable march of cosmic evolution. In the face of such boundless time, our own fleeting moments are but a whisper in the cosmic wind. Yet the enduring presence of these ancient giants invites a profound sense of perspective. The concept of time itself warps and distorts near a black hole's immense gravity. Imagine, if you will, a cosmic river. We perceive this river, the flow of time, as constant, as a steady, unwavering current carrying us all forward at the same pace. This is our everyday experience, the ticking of clocks, the passage of days, the rhythm of our lives. But the universe, in its infinite complexity and grandeur, rarely adheres to our simple, intuitive perceptions. Near the heart of a black hole, this steady river becomes a turbulent, swirling maelstrom, where the very notion of temporal flow bends and twists in ways that challenge our deepest understanding. This phenomenon is a direct consequence of Einstein's theory of general relativity, a masterful framework that describes gravity not as a force, but as the curvature of spacetime itself. Massive objects like stars, planets, and indeed black holes warp the fabric of spacetime around them. The more massive and dense an object, the more pronounced this warping becomes. A black hole, with its unfathomable density concentrated into an infinitely small point, creates an extreme curvature. This curvature affects not only the path of light and matter, but also the passage of time. For an observer far away from a black hole, time would appear to tick along at its normal rate. However, for an observer approaching the black hole, or for an object falling towards it, time would appear to slow down dramatically relative to the distant observer. This is not an illusion. It is a fundamental aspect of how gravity influences the temporal dimension. As an object gets closer to the event horizon, the point of no return, the gravitational pull becomes so intense that spacetime is stretched and distorted to an extreme degree. Time in this region dilates, meaning it passes more slowly. If one could hypothetically observe a clock falling into a black hole from a safe distance, that clock would appear to tick slower and slower as it approached the event horizon. From the perspective of the falling clock, however, time would continue to pass normally. But for the distant observer, the clock would seem to freeze at the event horizon, never quite crossing it, its signal fading into oblivion as it succumbs to the black hole's embrace. This temporal distortion is a stark reminder that time is not an absolute, universal constant, but rather a relative dimension, intricately woven with space and profoundly affected by the presence of mass and energy. The immense gravity of a black hole creates a region where the future is irrevocably dictated by the singularity, and the past becomes an ever-receding memory, stretched and distorted beyond recognition. The very fabric of existence, time and space, are contorted into a cosmic knot, a testament to the power of gravity to reshape reality itself. Near the embrace of a black hole, time, our constant companion, becomes a fluid, yielding to the profound pull of gravity, reminding us that our perception of its steady march is but a gentle ripple on a vastly deeper cosmic ocean. Inside a black hole, our conventional understanding of space and time breaks down. The interior of a black hole is a realm where the familiar laws of physics, as we understand them from our everyday experience, cease to apply in their usual forms. Imagine crossing the event horizon, that invisible boundary beyond which escape is impossible. What lies within is not a void, but a region of such extreme gravitational distortion that the very fabric of spacetime is fundamentally altered. Our concepts of direction, of movement, of cause and effect become profoundly warped. Within this enigmatic domain, space and time are not merely bent. They are, in a sense, interchanged. The direction that we perceive as forward in time, the arrow of progression from past to future, becomes inseparable from the spatial dimension pointing towards the singularity at the black hole's heart. Every path, every possible trajectory, inevitably leads inward towards this ultimate point of infinite density. There is no turning back, no standing still, no escape from the relentless pull. It is a place where the very notions of here and when become entangled in a way that defies our intuition. The immense gravity creates tidal forces so powerful that they would stretch and compress any object, a process often referred to as spaghettification, reducing matter to its most fundamental components. But beyond the physical destruction, it is the dissolution of our temporal and spatial frameworks that is most disorienting. Time, as we measure it, as we feel it, as it governs our lives, is no longer a consistent, flowing river. Instead, it is a dimension that is being compressed, twisted, and ultimately consumed by the overwhelming gravitational well. The singularity itself is predicted to be a point where all matter and energy that has fallen into the black hole is crushed into an infinitely small volume, a place where density and curvature become infinite, and our current physical theories reach their absolute limit. It is here, at this precipice of the known universe, that the familiar narrative of reality dissolves into an incomprehensible enigma. The very concept of existence within such a boundary challenges our deepest assumptions about the universe and our place within it. Within the crushing embrace of a black hole, the river of time merges with the currents of space, carrying all towards an unknown, singular destination. The ultimate fate of matter that falls into a black hole remains a profound mystery. When we speak of the ultimate fate of matter that plunges into the abyss of a black hole, we are venturing into the very frontiers of our scientific understanding, a place where established laws begin to shimmer and fade. Imagine, if you will, a cosmic object so dense, so gravitationally potent, that it warps the very fabric of space-time around it. This is the black hole, a celestial enigma that has captivated and confounded scientists for decades. The journey into a black hole is not a gentle descent. It is a relentless pull, a one-way passage through a boundary known as the event horizon. Once this invisible threshold is crossed, there is no turning back. The immense tidal forces, often described as spaghettification, would stretch any object, even a star, into long, thin strands of matter before it reaches the singularity at the black hole's heart. But what happens at the singularity? This is where our current models, based on Einstein's theory of general relativity, encounter a significant limitation. General relativity predicts a point of infinite density and zero volume, a place where space-time curvature becomes infinite. However, physicists widely believe that a more complete theory, one that successfully unifies gravity with quantum mechanics, is needed to accurately describe the conditions at the singularity. Quantum mechanics, which governs the behavior of matter and energy at the smallest scales, suggests that infinities in physical descriptions are usually a sign that our theory is incomplete. Therefore, the fate of matter at the singularity is not simply to be crushed out of existence, but rather to exist in a state governed by principles we do not yet fully comprehend. Some theoretical frameworks propose that information is not lost, but rather encoded in some subtle way at the event horizon, a concept known as the holographic principle. Others suggest that the singularity itself might be a gateway to another region of space-time, perhaps even another universe, though these ideas remain highly speculative. The extreme conditions within a black hole might also lead to matter being transformed into a state of pure energy, or perhaps a form of matter that is fundamentally different from anything we currently recognize. The process of Hawking radiation, where black holes are theorized to slowly emit particles and lose mass over unfathomably long periods, further complicates the picture. While this radiation is incredibly weak for stellar mass and supermassive black holes, it suggests that even these colossal entities are not truly eternal and will eventually evaporate. If a black hole evaporates completely, what becomes of the matter and energy that fell into it? Does it simply cease to exist, or is it re-released into the cosmos in a transformed state? The very definition of fate becomes blurred when we consider the extreme warping of time near a black hole. For an observer falling in, time would continue to tick, albeit in a profoundly altered manner. For an external observer, the falling object would appear to slow down as it approaches the event horizon, never quite crossing it, eventually fading from view as its light is redshifted into oblivion. This discrepancy in the perception of time further underscores the alien nature of black hole physics. The journey into a black hole is, in essence, a journey into the unknown, a testament to the vastness of cosmic mysteries that still lie before us. The sheer power and enigmatic nature of these celestial bodies remind us that even within the seemingly ordered universe, there are realms where our current knowledge reaches its limit, inviting us to ponder the extraordinary possibilities that await discovery. The journey into a black hole is a passage into the profound silence where known physics whispers its last, leaving us to marvel at the universe's most enigmatic transformations. Supermassive black holes reside at the centers of most galaxies, including our own. Imagine, if you will, the grand architecture of the cosmos, the sprawling nebulae, the luminous star clusters, the vast, silent expanses of intergalactic space. Within this magnificent tapestry, there exists a profound, unseen anchor, a gravitational heart beating at the very core of nearly every galaxy. These are the supermassive black holes, entities so colossal, so dense, that their influence shapes the evolution and structure of their galactic homes. Our own Milky Way galaxy, a swirling disk of billions of stars, is no exception. At its very center, buried deep within a dense region of stars and gas known as the galactic bulge, lies Sagittarius A, our galaxy's supermassive black hole. Its mass is estimated to be around 4 million times that of our Sun. To grasp this immensity is to stretch the limits of human comprehension. Consider that if our Sun were the size of a grain of sand, Sagittarius A would be a sphere with a radius of roughly 600 kilometers, larger than many countries. This isn't a theoretical construct. It's an observed reality, its presence inferred by the frantic orbits of stars and gas clouds that dance around it, accelerating to incredible speeds as they are drawn into its gravitational embrace. These central behemoths are not merely passive observers of galactic life. They are active participants. The immense gravitational pull of a supermassive black hole can trigger waves of star formation, or conversely, its powerful jets of energy can suppress it, creating vast, intricate structures of gas and radiation that stretch for thousands of light years. The very existence of these colossal objects at the heart of galaxies suggests a co-evolutionary dance, a process where the black hole and its host galaxy grow and influence each other over cosmic timescales, shaping the galactic landscape we observe today. The study of these central engines provides us with invaluable insights into the fundamental forces that govern the universe, pushing the boundaries of our understanding of gravity, space-time, and the very nature of existence. They are the silent, powerful directors of cosmic ballets, orchestrating the grand movements of stars and gas, and their presence is a testament to the astonishing power and complexity of the universe. The journey to understanding these central giants is a journey into the deepest mysteries of galactic dynamics and the profound influence of gravity on the grandest scales. They are the unseen architects, shaping the very fabric of our cosmic neighborhoods. In the silent, vast heart of our galactic home, a colossal gravity reigns, a testament to the universe's enduring power to forge immense wonders from the remnants of stars. The Milky Way's central black hole, Sagittarius A, is a silent cosmic anchor. At the very heart of our home galaxy, the Milky Way, lies an entity so profound, so immense, that it shapes the very structure and dynamics of the celestial island we inhabit. This is Sagittarius A, or SGRA for short, a supermassive black hole whose presence, though invisible to our direct sight, is undeniably felt across hundreds of thousands of light years. Imagine, if you will, a cosmic anchor, not forged of metal or rope, but of pure, unadulterated gravity, holding together billions upon billions of stars, nebulae, and interstellar dust clouds. This is not a void of emptiness, but a nexus of incredible density, a point where the fabric of spacetime is stretched and contorted to its absolute limit. SGRA is estimated to possess a mass equivalent to about 4 million times that of our Sun. To put this into perspective, if our Sun were the size of a grain of sand, SGRA would be a sphere encompassing the entire planet Earth. Yet, despite this colossal mass, it is remarkably compact. Its event horizon, the boundary beyond which escape is impossible, is only about 24 million kilometers in diameter. This is a diameter that, while vast by human standards, is minuscule compared to the sheer scale of the galaxy it governs. The stars closest to SGRA orbit it at astonishing speeds, some completing a full revolution in mere years, a cosmic ballet dictated by its overwhelming gravitational pull. These stars, observed over decades, have provided astronomers with irrefutable evidence of its existence, their erratic and rapid movements painting a clear picture of an unseen, massive object at the galactic core. The light from these stars, as it passes near SGRA, is subtly bent, a phenomenon predicted by Einstein's theory of general relativity, further confirming the black hole's gravitational might. The process of matter falling into SGRA is not a gentle descent, while the black hole itself is not actively feeding in a way that would create a spectacular, galaxy-devouring spectacle. There are occasional streams of gas and dust that are pulled towards it. As this material spirals inward, it heats up to incredibly high temperatures, emitting radio waves and X-rays that we can detect. This accretion disk, though relatively small compared to the black hole's mass, is a testament to the energetic processes occurring at the galactic center. The very existence of SGRA has profound implications for our understanding of galaxy formation and evolution. It is believed that most, if not all, large galaxies host supermassive black holes at their centers, suggesting a co-evolutionary relationship. These black holes may play a crucial role in regulating star formation within their galaxies, their powerful outflows of energy and matter influencing the surrounding gas and dust. The study of SGRA is a window into the extreme physics of gravity and spacetime, pushing the boundaries of our knowledge. It is a constant, silent force, a gravitational heart beating at the center of our cosmic home, a silent, cosmic anchor holding our galaxy together through the unfathomable depths of space and time. Our galaxy's heart, a silent giant, anchors the swirling dance of a million suns. Stellar black holes are formed from the collapse of massive stars. Imagine, if you will, a star far grander than our own sun, a celestial titan burning with an intensity that dwarfs its kin. These are the stars destined for a dramatic ultimate transformation. For billions of years, they engage in a furious dance of fusion, their cores a crucible where lighter elements are forged into heavier ones. Hydrogen becomes helium, helium becomes carbon, and so on, a cosmic alchemist's dream unfolding in the heart of a star. This relentless fusion generates an outward pressure, a magnificent outward push that perfectly balances the inward pull of gravity, the star's own immense weight. It is a state of equilibrium, a delicate cosmic ballet that sustains these luminous giants for eons. But even the most powerful fusion processes have a limit. Eventually, these colossal stars begin to run out of fuel. They can no longer generate enough outward pressure to counteract the relentless, crushing force of their own gravity. When a star of sufficient mass, typically more than 8 to 10 times the mass of our Sun, reaches this critical point, its core begins an irreversible collapse. The outer layers, momentarily bewildered by the loss of support, rush inward. This catastrophic implosion happens with astonishing speed, compressing the stellar remnant into an impossibly small volume. The energy released during this violent collapse is immense, often manifesting as a supernova, a breathtaking explosion that can briefly outshine an entire galaxy, scattering the stars' heavier elements, the very building blocks of future worlds and life, across the vast expanse of space. What remains after this spectacular demise is the core, an object so dense, so gravitationally potent, that it becomes a black hole. The gravity here is so extreme that nothing, not even light, can escape its clutches once it crosses a specific boundary known as the event horizon. This is not a void, but a region of spacetime where gravity has become the ultimate ruler, bending, twisting, and ultimately trapping everything that ventures too close. The very fabric of reality is warped, and the stellar remnant, once a radiant beacon in the cosmos, transforms into an invisible, yet incredibly powerful entity. The process is a stark reminder of the universe's capacity for both magnificent creation and profound destruction, a cycle of stellar life and death that continuously reshapes the cosmic landscape. These stellar black holes, born from the fiery demise of giants, are scattered throughout our galaxy, silent witnesses to the grand, evolutionary narrative of the universe, each a monument to the ultimate power of gravity. They are the remnants of stellar lives lived to their absolute fullest, ending not in a gentle fading, but in an explosive, transformative event that births a new, enigmatic object into existence, a dark heart beating within the luminous tapestry of the cosmos. Their formation is a testament to the fundamental forces at play, a dramatic conclusion to a star's long and arduous journey through the universe, leaving behind an object that defies our everyday understanding of existence. From the fiery heart of a dying giant, a new, invisible titan emerges, a testament to gravity's ultimate reign. Primordial black holes might have formed in the earliest moments of the universe. In the grand tapestry of cosmic evolution, our understanding often begins with the explosive birth of the universe itself, the Big Bang. We visualize a universe expanding from an incredibly hot, dense state, a singularity of unimaginable proportions from which all matter, energy, space, and time emerged. But within this primordial crucible, a fascinating and still somewhat speculative idea arises: the potential existence of primordial black holes. These are not the black holes we typically imagine, born from the spectacular death throes of massive stars billions of years later. Instead, primordial black holes are hypothesized to have formed in the very first fractions of a second after the Big Bang. Imagine the universe in its infancy, a chaotic, incredibly energetic and fluctuating soup of fundamental particles and intense gravitational forces. In such an environment, it's theorized that localized regions of this superdense plasma could have, through sheer random chance and the overwhelming power of gravity, collapsed in on themselves to form black holes. These would have been incredibly varied in mass, unlike stellar black holes which are typically bound by the mass of their progenitor stars. Some primordial black holes could have been as small as an asteroid, while others might have been as massive as stars, or even larger. The conditions then were so extreme, so unlike anything we can replicate or even fully comprehend today, that the very fabric of spacetime might have been prone to such dramatic collapses. The early universe was a period of rapid inflation and phase transitions, where energy was being converted into matter, and gravity was the dominant force shaping its nascent structure. It's within this tempestuous genesis that the seeds of these ancient, perhaps phantom, black holes could have been sown. The idea of these early cosmic collapses adds another layer of profound mystery to our understanding of the universe's origins, suggesting that the entities we now associate with the deep, dark voids of space might have been present from the very beginning, a silent testament to the universe's tumultuous birth. The very existence of these hypothetical objects challenges our linear perception of cosmic development, hinting at a more complex and perhaps cyclical beginning. They are whispers from the dawn of creation, remnants of a time when the universe was still learning its own fundamental laws, a time of extreme density and unimaginable energy, where gravity could sculpt not just the large-scale structure, but also the very points of no return that would endure for eons. Their potential presence suggests that the universe was not merely expanding, but was actively and violently forming structures, even those as extreme as black holes, within its first fleeting moments. This concept opens up a vast frontier of cosmological inquiry, pushing the boundaries of our observational and theoretical capabilities as we seek to understand whether these ancient cosmic entities truly played a role in the universe's earliest chapters, shaping its destiny from its very inception. The possibility that these enigmatic objects could have been born in the instant after the Big Bang, from the raw, untamed energy of the nascent cosmos, is a humbling reminder of the immense forces that govern the universe's genesis. Their potential formation in such extreme and fleeting conditions speaks to the chaotic and dynamic nature of the universe's earliest moments, a period where the fundamental forces were so potent that they could forge even the most extreme of cosmic structures. And so, the universe's first moments may have held the seeds of its deepest mysteries, a silent promise of the cosmic darkness to come. The universe's expansion is accelerating, pushing galaxies further apart. For decades, the scientific community believed that the universe's expansion, set in motion by the Big Bang, was gradually slowing down. It was a natural assumption, akin to throwing a ball into the air and expecting gravity to eventually bring it back down, or at least to halt its ascent. We envisioned a cosmic tug-of-war between the initial outward momentum of the Big Bang and the inward pull of gravity exerted by all the matter within the universe. The question was simply about the balance of these forces. Would gravity win, leading to a collapse, or would the expansion continue, albeit at a decelerating pace, perhaps forever? Then, in the late 1990s, two independent teams of astronomers, studying distant supernovae, exploding stars that serve as cosmic lighthouses, made a discovery so startling, so counterintuitive, that it fundamentally reshaped our understanding of the cosmos. They found that, far from slowing down, the expansion of the universe is actually accelerating. This means that the rate at which galaxies are moving away from each other is not decreasing, but increasing over time. Imagine a car that, instead of applying the brakes as it goes uphill, suddenly slams on the accelerator. This is the cosmic equivalent. This acceleration implies the existence of a mysterious force or energy that is actively pushing space itself apart, overcoming the gravitational pull of all the matter. This unknown entity has been given the name dark energy. We cannot see it, we cannot directly detect it, yet its influence is profound and pervasive, making up an estimated 68% of the total energy content of the universe. The implications of this accelerating expansion are staggering. It suggests a future where galaxies not only recede from us, but do so at ever-increasing speeds. Eventually, galaxies beyond our local group will recede so rapidly that their light will no longer be able to reach us, effectively disappearing from our observable universe. The cosmos, once perceived as a potentially contracting or at least slowing entity, is now understood as a dynamic system in a state of ever-increasing outward motion, driven by an unseen, pervasive energy that dictates its ultimate fate. This discovery, awarded the Nobel Prize in Physics in 2011, opened up a vast new frontier of cosmological inquiry, forcing us to confront the limits of our knowledge and the sheer, astonishing scale of the universe's unfolding story. The cosmic dance is not winding down. It is, in a sense, speeding up, carrying us all further into the unknown. This accelerating outward surge reveals a universe not merely expanding, but actively stretching itself towards an ever greater, ever emptier future. Heat death is one proposed ultimate end of the universe, a state of maximum entropy. Imagine a universe that has continued to expand for an unimaginable duration, so long that the very concept of time as we understand it begins to lose its familiar anchors. Galaxies, once vibrant collections of stars, have drifted so far apart that their light no longer reaches one another. The grand cosmic ballet, the swirling dance of matter and energy, has slowed to an almost imperceptible crawl. In this far-future scenario, known as heat death, the universe approaches a state of thermodynamic equilibrium. This means that all energy has spread out as evenly as possible, and there are no more temperature differences to drive any sort of work or change. Think of it as the ultimate diffusion, where every particle is dispersed, every gradient has flattened, and the universe has reached a kind of cosmic stillness. The fundamental law of thermodynamics, the second law, states that in any closed system, entropy, a measure of disorder or randomness, tends to increase over time. In the context of the entire universe, if it is a closed system, this inexorable increase in entropy leads to a state where all usable energy has been depleted. Stars, the engines of cosmic light and heat, will have long since exhausted their fuel. Black holes, while incredibly dense and energetic in their own right, will also eventually begin their slow decay through Hawking radiation, a process that takes an astronomically long time. Even these behemoths will fade, their immense gravity eventually dissipating into a faint whisper of particles. The universe will become a vast, cold, and dark expanse, populated by a sparse scattering of fundamental particles and perhaps the lingering echoes of exotic matter. There will be no more stellar explosions, no more nebulae forming new stars, no more galaxies colliding. The vibrant dynamism that characterizes our current universe will be replaced by an almost absolute uniformity. Every region of space will be at virtually the same, incredibly low temperature, a cold that far surpasses anything we experience on Earth. The concept of work in the thermodynamic sense, the ability to do something to create change, will cease to exist because there are no energy gradients to exploit. It's a state of ultimate peace, perhaps, but also of ultimate inertia. The universe, in this view, doesn't end with a bang, nor necessarily with a whimper, but with a slow, gentle fade into an eternal, unchanging equilibrium. This is not a sudden collapse, but a gradual, almost imperceptible winding down, where the cosmic clock has effectively stopped ticking because there is no more energy to power its mechanism. The very fabric of reality, stretched thin and uniform, will offer no further possibilities for complexity or evolution. It is a scenario that pushes the boundaries of our imagination, a glimpse into a potential future where the universe has achieved its ultimate static state of being. This profound stillness, this absence of all activity, is the essence of heat death. It is the universe at its most diffuse, its most uniform, its most final in a quiet sense. In the vast, silent theater of the cosmos, heat death paints a picture of ultimate diffusion, where the universe's last breath is a sigh of perfect, unchanging calm. The Big Rip is another scenario where dark energy tears apart all structures. Imagine, for a moment, a universe not slowly fading into a cold, uniform stillness, but one that experiences a violent, ultimate unraveling. This is the unsettling yet fascinating possibility known as the Big Rip. It's a cosmic drama that unfolds not with a gentle sigh, but with a furious, accelerating expansion driven by an increasingly potent form of dark energy. Our current understanding of the universe suggests that it is expanding, and that this expansion is, in fact, accelerating. This acceleration is attributed to a mysterious force we call dark energy, which seems to permeate all of space and acts in opposition to gravity. While the exact nature of dark energy remains one of the greatest enigmas in modern cosmology, theoretical models explore various possibilities for its behavior over immense timescales. One such model posits that dark energy is not a constant, but rather something that grows stronger as the universe ages. This hypothetical form of dark energy is often referred to as phantom energy. If dark energy is indeed phantom energy, its repulsive force would not just counteract gravity, it would eventually overwhelm it, and not just on the grandest galactic scales, but on progressively smaller ones. In the initial stages of this scenario, the accelerating expansion would continue to push galaxies further and further apart, faster than the speed of light, rendering them invisible to one another. This would lead to a universe where each galaxy becomes an isolated island, its inhabitants unable to observe any other celestial bodies. But the Big Rip doesn't stop there. As the phantom energy continues to intensify, its grip would tighten, reaching out to encompass ever smaller structures. The gravitational bonds holding galaxy clusters together would be the next to succumb, followed by the individual galaxies themselves. The stars within these galaxies would be ripped from their orbits, flung outwards into the void. Then, the very fabric of the solar systems would begin to fray. Planets would be torn from their stars, and the stars themselves, once majestic celestial furnaces, would be rent asunder. The force of the Big Rip would continue its relentless advance, reaching down to the very atomic level. Molecules would be broken apart, atoms would be ripped into their constituent subatomic particles, and eventually, even these fundamental particles would be torn apart. The universe in this scenario would not end in a quiet demise, but in a cataclysmic tearing, a final, violent crescendo where all structure, all form is annihilated. It paints a picture of an end that is not a dissolution into nothingness, but a violent disintegration, a cosmic shredding of reality itself. The implications are profound, suggesting that the ultimate destiny of the cosmos could be a state of absolute, unrecoverable fragmentation. In this tearing of all things, the universe's story concludes not in stillness, but in an ultimate, explosive undoing. The Big Crunch suggests a universe that collapses back into a singular point. This idea, once a prominent contender in cosmological models, presents a dramatic inversion of the universe's explosive beginning. Imagine, if you will, a cosmic breath inhaled rather than exhaled. In this scenario, the expansion that has carried galaxies apart for billions of years would eventually halt, its momentum overcome by the relentless pull of gravity. The fundamental force that binds stars and planets would, on a universal scale, begin to draw everything back together. Galaxies, once distinct islands in the cosmic ocean, would begin to drift towards one another, their relative speeds increasing as the fabric of spacetime itself contracted. Clusters of galaxies would merge, then superclusters, until the entire observable universe was on a collision course with itself. The energy of this cosmic collapse would be immense, far surpassing any forces we witness today. Temperatures would rise dramatically, stars would be torn apart, and the very atoms that compose matter would likely be shredded. As the universe compressed, the density of everything within it would skyrocket. The space between particles would shrink, and the conditions would become increasingly extreme. It is theorized that this process would continue, reversing the cosmic expansion, until all matter and energy were squeezed back into an incredibly hot, dense, and infinitesimally small point. A singularity, much like the one from which the universe is believed to have originated in the Big Bang. This cyclical view of the universe, where a big crunch leads to another Big Bang, was a captivating thought, suggesting an eternal cosmic ballet of expansion and contraction. However, current observations of the universe's accelerating expansion, driven by what we call dark energy, have made the Big Crunch scenario less likely in its purest form. The cosmic tug-of-war between expansion and gravity appears to be heavily weighted towards expansion, at least for the foreseeable future. Yet, the intellectual exercise of considering the Big Crunch remains a powerful reminder of the dynamic and potentially transient nature of the cosmos, and how the fundamental forces can orchestrate grand, if ultimately unlikely, finales. It paints a picture of a universe that, rather than fading into an eternal, cold darkness, might instead experience a fiery, ultimate embrace. In the silent echo of a universe returning to its primal seed, even the grandest collapse whispers of beginnings yet unseen. The final black hole scenario envisions a universe dominated by these cosmic entities. Imagine a cosmos that has long since exhausted its stellar fuel, where galaxies have drifted apart to such an extent that their light can no longer reach one another, and where the very fabric of space-time has stretched and thinned into a profound, almost unimaginable emptiness. In this distant, almost alien future, the universe is not necessarily devoid of all structure, but rather, its remaining structures are of a fundamentally different nature. The grand, luminous galaxies of today, teeming with billions of stars, will have long since faded. The vibrant nebulae, the incandescent stellar nurseries, the fiery hearts of active stars, all these will have become relics of a bygone era. What will remain, enduring through eons that dwarf human comprehension, are the black holes. These enigmatic objects, born from the violent deaths of stars or perhaps from the even more fundamental processes of the early universe, possess an unparalleled longevity. While they are theorized to slowly evaporate through the faint whisper of Hawking radiation, this process is so extraordinarily slow that for all practical purposes, they can be considered eternal on the timescales we are contemplating. The universe, in its final stages, might become a vast, dark expanse, sprinkled with an ever-decreasing number of these celestial behemoths. These black holes, from the stellar remnants scattered throughout the void to the colossal supermassive black holes that may still anchor the remnants of galactic cores, will be the ultimate inheritors of existence. They will be the silent, patient observers of a universe that has finally settled into its most fundamental, and perhaps most desolate, state. The cosmic dance of creation and destruction, of light and shadow, will have largely concluded, leaving behind these enigmatic gravitational wells as the sole, enduring monuments to the universe's grand and ultimately somber history. The universe, in this final act, would be a testament to the enduring power of gravity, a silent testament to a time when stars blazed and galaxies collided, now reduced to an almost incomprehensible stillness, where the only significant cosmic actors are these ultimate gravitational prisons, slowly, imperceptibly, fading into the infinite. The light of stars will have long since ceased to travel, the echoes of the Big Bang will have long since dissipated, and the universe will have reached a state where its most prominent features are these profound absences of light and matter, these ultimate gravitational anchors that represent the very end of cosmic activity. The final black hole scenario paints a picture of a universe that has reached its ultimate equilibrium, a state of profound stillness and darkness, where the only remaining significant entities are these incredibly long-lived gravitational anomalies, the silent, enduring remnants of a once vibrant cosmos. They will be the final, solitary beacons in a universe that has finally succumbed to the ultimate forces of entropy and gravitational dominance, a cosmic graveyard where only the most robust structures can endure. The universe's ultimate destiny in this view is to become a vast, cold, and dark expanse, populated only by the slowly evaporating ghosts of black holes, the last vestiges of cosmic activity. The final black hole scenario presents a universe that has reached its ultimate, quiet conclusion, a profound stillness where these gravitational titans are the soul, enduring witnesses to the universe's long, majestic, and ultimately melancholic journey. In this silent, starless expanse, the black holes become the universe's final, quiet sentinels, holding within them the last vestiges of cosmic memory. The stars, those ancient beacons that have guided us through millennia, are not eternal. Their fiery brilliance, the very engines of creation and light, are fueled by a finite resource, nuclear fusion. For billions of years, stars have been diligently converting lighter elements, primarily hydrogen, into heavier ones like helium, releasing immense quantities of energy in the process. This ongoing cosmic alchemy is what illuminates our nights and warms our planets. However, this process, while seemingly boundless from our human perspective, is ultimately a finite endeavor. As the universe continues its relentless expansion, a grand cosmic ballet of creation and decay, the fuel within stars will inevitably dwindle. Imagine each star as a magnificent, self-contained furnace, burning through its celestial fuel with a majestic, yet inevitable progression. The hydrogen, the primary building block of stellar life, will be converted, and as it is consumed, the star's internal processes will change. For stars like our Sun, this process will eventually lead to a red giant phase, followed by the shedding of outer layers to form a planetary nebula, leaving behind a white dwarf, a dense, hot ember that slowly cools over eons. More massive stars undergo more dramatic transformations, culminating in supernovae that scatter heavier elements across the cosmos, seeding the next generation of stars and planets. But even these stellar giants will eventually exhaust their fuel, their brilliant lives ending in a spectacular, yet final, burst of energy. The universe, in its grand expansion, is carrying these stellar remnants further and further apart. As the galaxies recede, the light from distant stars will stretch and fade, their spectral signatures shifting towards the red end of the spectrum, a phenomenon known as redshift, a visual metaphor for the universe's growing emptiness. This expansion is not merely a spatial separation, it's a thermodynamic process. Over unfathomable timescales, the available energy in the universe will become more evenly distributed, leading to a state of maximum entropy, often referred to as heat death. In this future epoch, the vibrant furnaces of stars will have long since cooled, The universe will be a vast, dark expanse, populated by the cold, inert remnants of once brilliant celestial bodies. White dwarfs will have cooled into black dwarfs, theoretical objects that are so cold they emit no detectable radiation. Neutron stars, the incredibly dense cores left after some supernovae, will continue their silent, solitary existence. And black holes, those ultimate gravitational prisons, will remain, slowly accreting any stray matter that might still wander through the cosmic void. The magnificent tapestry of stars, so rich and vibrant in our present epoch, will unravel. The night sky, once ablaze with a dazzling array of stellar light, will gradually dim. This is not an end of activity, but a transition to a state of profound quiescence. The energetic processes that define our current cosmic era will cease, replaced by a pervasive, chilling stillness. The universe will become a vast, dark ocean, with only the faintest whispers of residual energy. The light that once painted the cosmos will have faded, leaving behind an almost absolute darkness, a testament to the inexorable march of cosmic time and the finite nature of stellar existence. This gradual dimming, this descent into a starless night, is a profound aspect of the universe's grand, unfolding narrative, a quiet prelude to an even deeper cosmic silence. The dimming of the stars is not a tragedy, but a natural, majestic conclusion to their brilliant cycles, leaving behind a universe whispering of its former glory. Black holes will then become the dominant, albeit slowly fading, structures. As the grand cosmic stage empties, as stars exhaust their nuclear fuel and fade into dim embers, as galaxies drift apart into the ever-expanding void, a subtle yet profound shift will occur in the universe's grand architecture. The bright, vibrant beacons of fusion will cease their energetic dance, leaving behind a universe increasingly dominated by shadows. These shadows, however, are not merely the absence of light, but rather the presence of an utterly different kind of cosmic power, gravity, concentrated to its absolute extreme. Black holes, born from the violent demise of stars and lurking at the hearts of galaxies, will, in this far-flung future, stand as the last bastions of significant mass and structure. They are the ultimate survivors, the cosmic entities that endure when all else has succumbed to the inexorable march of entropy and expansion. Their dominance will not be one of active creation or radiant brilliance, but rather a passive, yet immense gravitational presence. Imagine a vast, dark ocean, where the only discernible features are these colossal, unseen abysses, slowly, infinitesimally, shaping the emptiness around them. They will be the silent monuments to a universe that once teemed with life and light, now existing in a state of profound, almost unimaginable stillness. The universe will become a canvas painted in shades of near-absolute black, with these gravitational titans as the only, albeit slowly diminishing, brushstrokes. Their slow evaporation, a process so drawn out that it defies human comprehension, will be the only ongoing cosmic activity. This fading will be measured not in years, or even eons, but in timescales so immense that they stretch beyond our wildest imaginings, far surpassing the current age of the universe by an order of magnitude that is almost impossible to truly grasp. Each black hole, a remnant of a once vibrant star or a primordial cosmic event, will slowly leak its energy into the void, a process known as Hawking radiation. This emission is incredibly faint, a whisper of particles escaping the gravitational embrace. For the largest supermassive black holes, the time it takes for them to completely evaporate is estimated to be something like 10–100 years, a number so staggeringly large it's often referred to as a googolplex of years. To put that into perspective, the current age of the universe is a mere 13.8 billion years, a blink of an eye compared to the lifespan of a black hole. During this incredibly protracted epoch, these entities will be the last significant concentrations of matter and energy. They will be the ultimate cosmic anchors in a universe that is otherwise dissolving into a uniform, cold, and dark expanse. Their gravitational pull will still influence the sparse distribution of stray particles and the occasional wandering proton, but even this influence will wane as they, too, slowly diminish. The cosmic landscape will be one of profound emptiness, where the only remaining structures of consequence are these enigmatic, slowly disappearing gravitational wells. This future epoch is often referred to as the degenerate era or the black hole era, a testament to their final, albeit fading, reign. It is a future that highlights the fundamental nature of gravity as a persistent force, even as other forces and phenomena cease to exist. The dominance of black holes in this final chapter of the universe is not a sign of their power in the way we might think of a star's brilliance, but rather a reflection of their enduring nature in a universe that is otherwise winding down. They are the last echoes of cosmic complexity, the final structures to yield to the universe's ultimate fate. In this eventual, silent cosmos, the immense gravity of black holes will be the last significant force shaping the void, a slow, fading testament to a universe that was once filled with light and motion. The evaporation of black holes through Hawking radiation is a slow, drawn-out process. Imagine, for a moment, the immense gravitational embrace of a black hole. It is a cosmic paradox, a region where gravity is so profoundly strong that nothing, not even light, can escape its grasp once it has crossed a certain boundary. This boundary, the event horizon, is often perceived as an impenetrable barrier, a one-way door into oblivion. For decades, this was the prevailing, and indeed the only scientific understanding of these enigmatic celestial objects. They were thought to be eternal, immutable entities, slowly accreting matter and growing, but never diminishing. Their existence seemed to be a permanent fixture in the grand tapestry of the cosmos, a testament to the ultimate power of gravity. However, the elegant, yet often counterintuitive, landscape of quantum mechanics, when applied to the extreme conditions near a black hole, revealed a surprising truth. It suggested that these cosmic titans might not be as eternal as they appear. The concept, pioneered by the brilliant physicist Stephen Hawking, introduced the idea of Hawking radiation, a subtle yet persistent emission of particles from the vicinity of the event horizon. This radiation, though incredibly faint for stellar mass and supermassive black holes, implies a gradual, almost imperceptible, loss of mass and energy. It is a process so slow that it defies human comprehension, operating on timescales so vast they dwarf the current age of the universe. For a black hole of solar mass, the time it would take to evaporate completely is estimated to be around 1067 years. To put this into perspective, the current age of the universe is approximately 13.8 x 10^9 years. This means that a solar mass black hole would take roughly 1057 times longer to evaporate than the universe has existed. For supermassive black holes, the timescale is even more astronomical. The supermassive black hole at the center of our own Milky Way, Sagittarius A, is estimated to have a mass of about 4 million solar masses. Its evaporation time is calculated to be in the realm of 10–100 years. This number is so staggeringly large that it is difficult to even conceptualize. It is a duration that extends far beyond the lifespan of stars, beyond the existence of galaxies, and likely beyond any form of observable cosmic structure that we can currently imagine. The process of Hawking radiation arises from quantum fluctuations near the event horizon. In the vacuum of space, particle-antiparticle pairs are constantly popping into existence and annihilating each other. Near the event horizon of a black hole, it is possible for one particle of a pair to fall into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting particles. However, from the black hole's perspective, it is losing energy, and therefore mass, because the infalling particle carries away negative energy, effectively reducing the black hole's total mass. This is a truly profound concept. A black hole, the ultimate gravitational trap, is slowly leaking its very essence into the universe. It is a slow, inexorable dissipation, a cosmic sigh of relief as its immense gravitational power gradually wanes. The rate of this evaporation is inversely proportional to the black hole's mass. Smaller black holes evaporate much faster than larger ones. This is because the gravitational pull at the event horizon is weaker for smaller black holes, making it easier for quantum fluctuations to lead to particle escape. Therefore, in the far future, as the universe continues to expand and stars cease to form and die, the remaining black holes will be the last significant structures to exist, and they too will eventually fade away. This process is not a sudden explosion or a dramatic implosion, but rather a gentle, drawn-out dissolution, a slow surrender to the fundamental laws of quantum mechanics. It is a reminder that even the most seemingly permanent and powerful entities in the universe are subject to change, to a cosmic cycle of existence and eventual dissolution. The universe, in its final moments, will be a place of profound silence and darkness, with only the faintest whispers of radiation from the dying embers of these once mighty black holes. This slow evaporation, this cosmic fading, is a testament to the universe's enduring capacity for transformation, a gentle unwinding of its grandest structures. As the universe ages into an unfathomable twilight, even the most formidable gravitational prisons will slowly yield their energy, transforming into the faintest of whispers against the infinite canvas of existence. The universe's eventual state might be one of extreme cold and darkness, punctuated by faint radiation. Imagine, if you will, a cosmic tapestry that has unfurled over unimaginable eons. The vibrant hues of starbirth have long since faded, replaced by the deep, unending indigo of a universe in its twilight. This is the scenario of the far future, a state so distant that it stretches the very limits of our comprehension. It is a vision of extreme cold and profound darkness, a quiet culmination where the grand cosmic engine has all but sputtered out. The stars, those magnificent furnaces of light and heat that have illuminated galaxies for billions of years, will have long since exhausted their fuel. Red dwarfs, the longest-lived of our stellar kin, will have burned through their hydrogen, eventually cooling into inert white dwarfs, then further into cold, dark cinder-like remnants. Massive stars will have met their dramatic ends as supernovae, leaving behind neutron stars and black holes, but eventually, even these will cease their energetic activity. The galaxies themselves, once bustling metropolises of celestial activity, will become vast, desolate expanses, their stellar populations depleted, their nebulae dispersed. The very fabric of space, stretched thin by the relentless expansion, will become a chilling void. Temperatures will plummet towards absolute zero, a state where all thermal motion, the very essence of heat and energy as we understand it will have virtually ceased. This is not a sudden, violent end, but a slow, drawn-out surrender, a gradual dimming of the cosmic lights. Yet even in this profound stillness, there might be whispers of activity. The universe will not be entirely devoid of energy. The lingering echoes of past cosmic events, the faint remnants of particle interactions, and crucially, the slow, almost imperceptible decay of matter itself, will contribute to a pervasive, albeit infinitesimally faint, radiation. This radiation, a ghost of a more energetic past, will be the only testament to the universe's former dynamism. Even protons, the fundamental building blocks of atomic nuclei, are theorized to decay over timescales so immense that they dwarf the current age of the universe. This proton decay, if it occurs, would release a trickle of energy, a final, fading hum in the cosmic silence. And then there are the black holes, the ultimate repositories of matter and energy. While they too are predicted to evaporate through Hawking radiation, this process is extraordinarily slow. For the most massive black holes, this evaporation will take longer than the universe has existed, meaning that in the far future they will still be present, albeit slowly diminishing. The radiation emitted during this final, drawn-out evaporation will be the last vestiges of organized energy in the cosmos, a final, faint glow before the ultimate, eternal darkness. This state is often referred to as the heat death of the universe, not in the sense of a fiery demise, but a descent into a state of maximum entropy, a uniform distribution of energy where no further work can be done, no change can occur. It is a universe at rest, a cosmic slumber from which there may be no awakening. The cold embrace of this future is a humbling reminder of the finite nature of all things, even the grandest celestial spectacles. In this vast, cold expanse, where the last embers of starlight have long since winked out, we find a profound stillness, a universe cradled in an infinite, silent night, where the faintest whispers of existence are the final lullabies of creation. The concept of end of time is tied to the ultimate thermodynamic equilibrium. The idea of an end of time is not necessarily a cessation of existence in a dramatic, cataclysmic burst, but rather a state of profound stillness, a cosmic twilight where the very engine of change grinds to a halt. This concept is deeply interwoven with a fundamental principle of physics, the second law of thermodynamics. This law, in its simplest form, states that in any closed system, the total entropy or disorder can only increase over time or remain constant. It never decreases. Imagine a perfectly organized room. Over time, without intervention, it will naturally become messier. Objects will be misplaced, dust will accumulate, and the overall state of disorder will rise. The universe in many ways can be considered such a grand, albeit infinitely complex closed system. As time progresses, energy disperses, structures break down, and the universe tends towards a state of uniform temperature and density, a state of maximum entropy. This is what scientists refer to as thermodynamic equilibrium. In such a state, there are no temperature differences, no pressure gradients, no imbalances whatsoever. And without these differences, without the potential for energy to flow from one place to another, the processes that we associate with time, change, motion, evolution, would simply cease. Stars would have long since burned out, black holes would have evaporated, and even subatomic particles would be spread so thinly, and at such uniform low energy levels that interactions would become vanishingly rare. The universe would become a vast, cold, and featureless expanse, bathed in a uniform, almost imperceptible glow of residual energy. It is a state of ultimate calm, a profound and absolute stillness where the arrow of time, driven by entropy's relentless march, finally points nowhere. This equilibrium is not an event, but a gradual, almost imperceptible fading into a state where the very concept of before and after loses its meaning, where the universe exists in an eternal, unchanging present. It is the ultimate quietude, a universe at rest, having expended all its potential for change. In this ultimate stillness, the universe finds its most profound rest, a quietude where the echo of existence fades into an eternal, unchanging now. Our perception of time is a human construct, deeply intertwined with physical processes. We experience time as a linear progression, a relentless march from past to present to future. This fundamental aspect of our consciousness, this feeling of duration and flow, is so ingrained that it often feels like an objective reality, an intrinsic property of the universe itself. Yet, when we delve into the depths of physics, particularly as we approach the extreme conditions we've been discussing, the colossal gravity of black holes, the vastness of cosmic timescales, we begin to see how profoundly our human perception of time is shaped by our own biological and physical existence, and how it differs from the more fundamental, and sometimes perplexing, reality described by science. Our bodies, after all, are biological machines operating within specific thermodynamic frameworks. Our hearts beat, our cells age, our brains process information sequentially. These internal rhythms create an undeniable sense of passage, a feeling of moments accumulating and transforming. This is the time of our lived experience, the time measured by clocks and calendars, the time that governs our daily lives, our memories, and our plans. It is a time woven from the fabric of our own being, a biological imperative that allows us to navigate our world, to learn, to grow, and to remember. But the universe, in its grandest and most extreme manifestations, operates on scales and under principles that can stretch, compress, and even fundamentally alter this familiar notion. For instance, Einstein's theories of relativity have shown us that time is not absolute. It is relative. It can dilate, meaning it can slow down, in the presence of strong gravitational fields or at speeds approaching that of light. This means that, for an observer near a black hole, time would pass much more slowly than for an observer far away. Their clocks would tick at different rates. This is not a trick of perception. It is a fundamental alteration of the space-time fabric. The very now, for one observer, might be in the distant past or future for another. This relativity of time is a cornerstone of modern physics, yet it stands in stark contrast to our intuitive, human experience of a universal, unwavering present. Furthermore, our understanding of causality, of cause and effect, is intrinsically linked to our linear perception of time. We assume that a cause must always precede its effect. This assumption is crucial for our ability to make sense of the world and to interact with it safely. However, in the bizarre quantum realm, and especially near the singularity of a black hole, where the rules of physics as we know them seem to break down, this strict temporal ordering can become blurred or even cease to be meaningful. The idea of a final black hole, a state where the universe has reached its ultimate thermodynamic equilibrium, also challenges our temporal concepts. If all processes have ceased, if there is no more energy to dissipate, no more change to occur, then what does time even mean? In such a state of absolute stillness and uniformity, the very notion of duration, of passage, of a sequence of events, would likely become meaningless. Our perception of time, therefore, is not a direct window onto the universe's fundamental nature, but rather a sophisticated interpretation, a biological and cognitive tool that has evolved to help us survive and thrive within our particular corner of space-time. It is a construct, albeit a remarkably effective one for our everyday lives, that is deeply shaped by the physical processes of our own existence. The universe, in its ultimate states, may operate in ways that transcend this human-centric framework, reminding us that our deepest intuitions about reality are often just that, intuitions, not necessarily universal truths. In the silent, timeless expanse of the cosmos, our human sense of moments passing is but a gentle whisper against the vast, indifferent backdrop of existence. In a universe devoid of activity, the very notion of time might lose its meaning. Consider the fundamental nature of what we perceive as time. It is not an inherent, independent entity marching forward regardless of circumstance, but rather a dimension intricately woven into the fabric of existence, deeply entwelled with motion, change, and the processes that define our reality. Our very experience of time is a product of these interactions. We measure its passage by the ticking of clocks, the aging of organisms, the decay of radioactive isotopes, the orbits of planets, and the very rhythm of our own biological functions. These are all manifestations of activity, of energy being exchanged, of matter transforming. Without such activity, without the dynamic interplay of forces and particles, the mechanisms by which we perceive and quantify time would cease to have any reference point. Imagine a universe utterly still, where no particle moves, no wave propagates, no energy is transferred. In such a hypothetical state, the concept of before and after would become meaningless. The progression from one moment to the next, the very essence of temporal flow, would have no observable or even conceptual basis. Time, as we understand it, is intrinsically linked to change. When all change ceases, when the universe reaches a state of absolute equilibrium or utter stillness, the very framework upon which our understanding of time is built would crumble. It is a thought experiment that pushes the boundaries of our intuition, suggesting that time might be an emergent property of a dynamic universe, rather than a fundamental constant that exists independently of it. The slow, almost imperceptible decay of black holes, even in the deepest cosmic future, represents a form of activity, however minuscule. But if even that activity were to cease, if the universe settled into a state of perfect, unchanging stillness, then time, as we know it, would indeed dissolve into a profound and eternal non-existence, a state where the clock has not just stopped, but where the very concept of a clock has no meaning. In the quiet stillness of absolute equilibrium, the river of time would cease its flow, leaving only an unchanging, timeless ocean. The final black hole scenario is a philosophical contemplation as much as a scientific prediction. The universe, in its grand and ceaseless dance of creation and dissolution, presents us with a tapestry woven from the threads of scientific inquiry and profound philosophical wonder. When we turn our gaze towards the ultimate fate of existence, towards the theoretical end of all things, we often find ourselves at the intersection of these two powerful disciplines. The notion of a universe ultimately dominated by black holes, each slowly radiating away their existence over eons so vast they defy comprehension, is a scientific prediction rooted in our current understanding of gravity, thermodynamics, and quantum mechanics. Yet, the implications of such a scenario ripple outwards, touching upon the very essence of meaning, purpose, and our place within the cosmic order. It is a concept that compels us to ask not just how the universe might end, but what does it mean for such an end to be conceivable? Consider the journey that leads us to this contemplation. We begin with the observable universe, a realm of galaxies, stars, and planets, governed by elegant physical laws. We extrapolate these laws, pushing them to their theoretical limits. We consider the relentless march of entropy, the tendency for systems to move towards disorder and equilibrium. We factor in the peculiar nature of black holes, regions where gravity is so immense that nothing, not even light, can escape. And then we imagine a universe that has long outlived its stellar nurseries, a cosmos where the last stars have flickered out, leaving behind a vast, cold expanse. In this desolate future, black holes, formed from the collapsed remnants of the most massive stars and perhaps even from the primordial soup of the early universe, would become the dominant, albeit slowly fading, structures. The scientific prediction here is that these black holes, while seemingly eternal, are not. Stephen Hawking's groundbreaking work revealed that black holes emit a faint thermal radiation, now known as Hawking radiation. This radiation carries away mass and energy, causing the black hole to slowly shrink and eventually evaporate. The timescale for this evaporation is staggeringly, almost unimaginably long. For a stellar mass black hole, it is on the order of 1067 years. For a supermassive black hole, like the one at the center of our own galaxy, the number is even more astronomical, 10,100 years. These are numbers so vast that they dwarf the current age of the universe, which is a mere 13.8 billion years, or 1.38x 1010 years. To put it into perspective, if you were to count one number every second, it would take you longer than the age of the universe to count to just 1 billion. To count to 10,100 would take a duration so immense that it transcends our ability to conceptualize it within the framework of our everyday existence. So, the scientific model paints a picture of a universe where, after trillions upon trillions of years, after the last flicker of light has faded, after all accessible energy has been converted into unusable forms, the only significant entities remaining would be these colossal, slowly dissipating gravitational wells. They would be the last vestiges of a once vibrant cosmos, continuing their nearly imperceptible evaporation into the void. This is the scientific prediction, a universe that ends not with a bang, but with a whisper, a slow fade into an ultimate state of thermodynamic equilibrium. However, the contemplation doesn't end with the scientific equations. This scenario prompts us to ponder the very nature of existence and meaning in a universe that eventually succumbs to such profound stillness and ultimate dissolution. What does it mean to contemplate an end that is so far removed from our current experience, so alien to our notions of time and change? It forces us to confront our own impermanence, our own fleeting existence against the backdrop of cosmic eternity. It encourages us to find value and significance not in the duration of our presence, but in the quality of our experience, in the moments of connection, understanding, and wonder that we share. The scientific prediction of the final black hole becomes a mirror, reflecting our own transient nature and prompting a deeper appreciation for the vibrant, dynamic universe we inhabit now. It is a thought experiment that, while rooted in rigorous physics, ultimately leads us to a more profound understanding of ourselves and our place within the grand, unfolding narrative of the cosmos. In this profound stillness, the universe's grand narrative finds its ultimate contemplative pause. Even in the deepest cosmic darkness, the principles of physics continue to operate. The universe, in its grandest, most ancient epochs, will eventually transition into a state of profound stillness. As stars exhaust their nuclear fuel and the energetic dance of creation wanes, a vast, cold darkness will begin to dominate. Galaxies will recede beyond the observable horizon, their light fading into an eternal twilight. Yet, even in this seemingly desolate future, the fundamental laws that govern reality will not cease their silent, unyielding work. The intricate tapestry of physics, woven from the very fabric of existence, will persist. Gravity, that invisible architect of cosmic structure, will still exert its influence, albeit on the remnants of what once was. The subtle, yet persistent, phenomenon of Hawking radiation will continue its slow, inexorable dissipation of black holes, the last bastions of concentrated energy. These cosmic entities, born from the dramatic collapse of stars, will very gradually shed their mass, transforming into faint whispers of energy over timescales, so immense they dwarf human comprehension. Even as the universe cools to near absolute zero, and the very concept of temperature loses its familiar meaning, the quantum fluctuations that underpin reality will still occur. These microscopic, unpredictable stirrings born from the vacuum itself are a constant reminder that even in the absence of grand phenomena, the universe remains a dynamic, albeit incredibly subtle, place. The principles of thermodynamics, the laws governing energy and its transformations, will still dictate the slow, inevitable march towards a state of maximum entropy, a universe where all energy is evenly distributed and no further work can be done. This is not an end to physics, but rather a final, serene state governed by its most fundamental tenets. The equations that describe the interactions of particles, the curvature of space-time, the propagation of energy, these will remain valid, describing a universe that has reached its ultimate tranquil equilibrium. The absence of light, of heat, of motion as we understand it, does not signify the absence of underlying order. Instead, it points to a universe that has achieved a state of perfect, albeit cold, harmony, dictated by the unwavering reign of physical law. This deep, cosmic darkness is not an absence of existence, but a testament to the enduring power and universality of the principles that define it. In the quietude of the universe's final moments, even as all else fades, the immutable laws of physics will continue their silent, eternal vigil, a gentle hum beneath the vast expanse of stillness. The universe's ultimate fate is a testament to the grand, unfolding narrative of existence. As we journey through the vast cosmic tapestry, contemplating the eventual dissolution of stars, the fading of galaxies, and the profound silence that may one day envelop all that we know, we are not merely observing a scientific prognosis. We are witnessing a profound unfolding, a narrative so grand it dwarfs our individual experiences, yet is intimately connected to our very being. The universe, in its relentless march towards equilibrium or perhaps some other cosmic denouement, reveals a story that is both awe-inspiring and deeply humbling. It is a story written in the language of physics, etched in the fabric of space-time, and played out over timescales that beggar the imagination. Each stellar explosion, each gravitational dance, each quantum fluctuation contributes a sentence, a paragraph, to this eternal saga. The very laws that govern the smallest particles also dictate the grandest cosmic destinies. This is not a story of random chaos, but of an intricate, interconnected system, evolving according to fundamental principles. The end, in whatever form it may take, will be a direct consequence of the beginning, a testament to the initial conditions and the enduring power of physical laws. To understand the potential end of the universe is to understand the complete arc of its existence, from the fiery birth to the ultimate, serene conclusion. It is a narrative that speaks of transformation, of cycles, and of the enduring essence of reality itself. We are, in a very real sense, witnesses to this cosmic story, participants in its grand unfolding. The ultimate fate of the universe, therefore, is not just an abstract scientific concept. It is a profound reflection of the continuous, evolutionary process that defines existence. It is a testament to the inherent dynamism and the ceaseless transformation that is the very essence of reality. The universe's grand narrative, from its explosive inception to its potential quietude, is a continuous, unbroken thread of cause and effect, a testament to the enduring power and majesty of cosmic evolution. In this grand unfolding, our own existence, though fleeting, is a precious and integral chapter. Contemplating such vast timescales can offer a unique perspective on our fleeting lives. When we turn our gaze towards the unfathomable expanse of cosmic history, towards the epochs that dwarf our own existence into mere blips, a profound shift in perspective can begin to occur. We speak of black holes, the ultimate cosmic enigmas, and their potential role in the universe's final act. But the mere contemplation of these scales forces us to confront our own temporal limitations. Our lives, measured in decades, are infinitesimally small against the backdrop of billions of years. The birth and death of stars, the slow dance of galaxies, the potential eons it takes for even the most colossal black holes to finally succumb to Hawking radiation. These are processes that operate on a temporal plane so alien to our daily experience that they almost defy comprehension. Yet, within this incomprehensibility lies a peculiar kind of solace. The anxieties that plague us, the urgent demands of the present moment, the perceived permanence of our struggles, they all begin to shrink when viewed against the canvas of cosmic time. The universe has witnessed countless beginnings and will witness countless endings, each unfolding at its own deliberate, majestic pace. Our fleeting lives, therefore, are not insignificant because they are short, but rather precious because they are intensely concentrated moments of experience within this grand, unfolding narrative. The very act of observing, of questioning, of seeking to understand these vast phenomena is a testament to the brief, brilliant spark of consciousness that we, as individuals, possess. This spark, though ephemeral, allows us to touch, however briefly, the immensity of existence. It grants us the capacity to marvel, to feel awe, and to find a quiet wonder in the face of the ultimate unknown. The universe's enduring nature, its capacity to persist and transform over unimaginable durations, can serve as a gentle reminder that even in our transience, we are part of something enduring and magnificent. The anxieties that bind us to the immediate often loosen their grip when we allow ourselves to be immersed in the contemplation of the truly immense. Our brief existence, when contextualized within the vastness of cosmic time, becomes not a source of despair, but an opportunity for profound appreciation, a chance to witness the grand, slow unfolding of reality from a unique, ephemeral vantage point. And in this vastness, our transient moments gain an unparalleled preciousness. The silence of the cosmos holds its own profound, awe-inspiring beauty. Imagine, for a moment, a universe where the grand symphony of creation has played its final note. The birth pangs of stars have ceased, The explosive finales of supernovae have long since faded into memory, and the vibrant chatter of active galaxies has dwindled to a whisper. What remains is a vast, immeasurable expanse, a canvas painted in shades of deep indigo and infinite black, punctuated only by the faint, ethereal glow of dying embers and the slow, inexorable march of entropy. This is the silence of the cosmos, a silence not of absence, but of a profound, almost sacred stillness. It is a silence that stretches across unimaginable distances, a silence that has witnessed the rise and fall of cosmic epochs, a silence that is, in itself, a testament to the sheer, unadulterated scale of existence. In this final act, the universe is not empty, but rather filled with a different kind of presence. It is the presence of immense, ancient structures, slowly succumbing to the fundamental laws that govern all things. Black holes, once fiery engines of cosmic transformation, now exist as colossal, slowly evaporating entities, their immense gravitational pull a silent, persistent force in the void. The faint whisper of Hawking radiation, the universe's gentle sigh as it releases its stored energy, is the only sound, a sound so subtle it is almost imperceptible, a lullaby sung by the very fabric of reality. Stars, the celestial beacons that have guided us for millennia, have long since exhausted their fuel, leaving behind the cold, dense remnants of white dwarfs, neutron stars, and the ultimate black holes. Galaxies, once bustling metropolises of cosmic activity, have become vast, sprawling nebulae of stellar debris, their constituent parts drifting further and further apart, their once vibrant cores now dark and quiescent. This profound silence is not a void to be feared, but a space to be contemplated. It is in this vast quietude that the true majesty of the universe can be appreciated. The sheer, unadulterated scale of it all, the eons of time that have passed, the immense forces that have shaped and reshaped everything we know, these are the elements that emerge in the cosmic hush. It is here that the individual human experience, so fleeting and so precious, can be placed within a grander, more enduring narrative. The silence of the cosmos, far from being empty, is a profound and awe-inspiring testament to the enduring power and quiet majesty of existence itself. Our calm exploration has covered the profound and the ultimate, venturing into the deep cosmic questions surrounding the final black hole and the potential end of time. We have reviewed the principles of gravitational collapse, the enigmatic nature of singularities, and the slow, majestic evaporation of black holes through Hawking radiation. We've considered the vast timescales involved, far beyond our human comprehension, and the various cosmological scenarios that might dictate the universe's ultimate fate, from the quiet stillness of heat death to the dramatic tearing of the Big Rip. Tonight, we have reviewed the principles of how these cosmic titans, the black holes, might become the last vestiges of structure in a universe that has long since exhausted its stars and energy sources. We've touched upon the theoretical limits of our current understanding, where the very fabric of space-time bends and breaks, and where our familiar concepts of time and space cease to apply. It is a contemplation that can feel both immense and intimately personal, a reminder of our place within a grand, unfolding narrative that stretches across an unimaginable expanse. By considering these vast, almost overwhelming cosmic finales, we can begin to find a sense of perspective. The struggles and stresses of our everyday lives, while undeniably real and significant to us, are but fleeting moments in the grand, silent opera of the cosmos. The anxieties that grip us can seem to diminish when placed against the backdrop of a universe that may eventually fade into a state of ultimate, serene equilibrium. This understanding is not meant to diminish our experiences, but rather to offer a gentle, soothing balm, a reminder of the enduring beauty and order that exists, even in the face of ultimate endings. It is time to rest now. Allow the quiet wonder of these cosmic concepts to settle within you, to dissolve the tensions of the day, and to create a space for profound peace. You have explored the edges of existence, and in doing so have found a quiet haven within yourself. Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing your journey through the quiet wonders of the universe.